Hello guys, welcome to Solving Solution, your number one channel where you get solutions to all your solving problems academically and even on site. So today we are going to continue on our Traverse Computation series. However, we are going to take it a step further or a step higher than the normal Traverse Computation. Today we are going to consider blunder, like blunder. Yes, you got me right, blunder. Maybe a deliberate mistake or a mistake that was very expensive, whether you did it deliberately or not. You know, sometimes in site, when you observe your angles and maybe you measure your distances and you're reading it off to somebody who is booking it, you might tell the person 130 degrees 59 minutes 28 seconds. The person might just book 103 degrees 59 minutes 28 seconds. You know, 130 and 103 are very different, like they are so far apart. So if something like that happens, the person might not know it was not deliberate actually. Maybe he was tired or she was tired, or maybe he made a mistake, something happened, and then instead of that 130 the person recorded 103. You go back to the office, or maybe you go back to school, and then you wanted to carry out your computation, or let's say you started your computation, and when you go to your angular misclosure where you have to distribute your error, you now see that the misclosure you get there is very big, like it's not within the allowable limit. And sometimes the misclosure you get there might even be up to degrees, like you might be seeing some 10 degrees, 20 degrees. Didn't you work on site? Like, were you there to play, or did you go there to play? You know, it can be overwhelming, like, everything I did is now bad. So what do I do next? So what's the way forward? What am I going to do? Will I go back to site and re-observe all the points? Will I throw away everything I did? Will I start shouting for the person that booked? There are so many things that will come to your mind. However, today we are going to bring a solution to that particular or to that kind of problem. So now let's continue. This is a field data. It's actually still an extract of the field book from our previous we used on our previous videos. However, there was changes somewhere, and actually the changes will now affect our computation. So if you look at it, it's the observed angle, horizontal distance to the forward station. If you look at our list of coordinates, they are the same. However, on these our observed angles here, there is a particular angle that was observed in error. There was a station on which the angle here, a particular angle, was observed in error. So that is what we want to do. We want to detect that particular station, then go back to site and observe only that station. Observe the angle on that station alone, instead of observing angles on 1, 2, 3, 4, 5, 6. Instead of observing the angles on these 6 stations, we are just going back to site to observe the angles on that particular station. So we didn't know that we made a blunder on site. So we got to maybe the school or to the office and we started our computation. As we did our normal back computation of the controls, sorry if you don't get this, there is on the description section below you can find links to where we started the Traverse computation, how you carry out your back computation, arrangement of controls and all the rest of that. And you can also see it on this playlist, because this particular video will be on a playlist, and when you check the playlist you will see the other videos that are related to how we did this. So to avoid wasting of time, we had to do this before we bring it live on video here to show you guys. So now what we did was that, okay, we came back from site, okay, let's try and compute our data and see whatever we get. And we got to this point where we are supposed to do what? We are supposed to get our angular misclosure, distribute it, and get our corrected bearing. So you know, on this particular line, which will be from, this is 22, so this will be 2.1. Let me indicate it. This will be 2.1. Then from 0.1 to what? To point 2, from point 2 to point 3, from point 3 to point 4, then from point 4 to kg21, from kg21 to what? To kg22. So if you remember on our previous videos, you will find out that this kg21 to kg22 serves as a check line. We know the bearing of this line. We also know the distance. If we can even get it from our what? From our back computation here, from kg21 to kg22. You know, the bearing we are supposed to get for this forward station is what? Is 30 degrees, 35 minutes, 49.9 seconds, which is 30 degrees, 49 minutes, 49.9 seconds. However, when we did our computation up to this point, we got 135. What's going on? You know, you say, maybe you made a mistake. We took our calculator again. We started the whole process. We got to this point. We still had 135. You know, 135 degrees and 30 degrees can never be, the misclosure can never be allowable. Let me not say anything more. So what do we do? In a situation like this, what you are going to do is, you just continue your computation without doing what? Without applying any correction. Now, these are some key points you need to note on this particular video. When you get to this point where you know that the misclosure is not within allowable limit, which definitely means it's a blunder. Which definitely means it's a what? It's a blunder. After you've carried out normal check, maybe you've done it 2 times, 3 times, and you're still having the same answer. So just know that a blunder has occurred. So what we want to do is that we want to detect the blunder. Blunder detection in Traverse Computation. So that's just the essence of this video. So you know that it's a blunder. So when there's a blunder, you don't apply any correction. So since you don't apply any correction, you won't have any corrected bearing. So this is a very, very important point you'll have to note on this particular video. Since there was the reason why I wrote this thing down here was because this is a check line. However, it was observed, but I was not supposed to write it, and I did not even write it before. But just for us to check or to see the comparison between this 135 degrees and this 30 degrees, I had to write it down here. So there was no correction, therefore there won't be any corrected bearing. Are we together? Okay, you said you got it. All right, now let's continue. So the horizontal distances, we've written them down. So what do we do next? How do we get our delta nothing and our delta easting? It's still the same step. You use your calculator. Remember, you want to get your rectangular coordinate, which is partial coordinate. So you use the rect function. You say distance, comma, the bearing. So in this case, since there is no corrected bearing, we are going to use our forward bearing. This is another point you have to note. It's just like a build up to the first one. The first one was that we did not have any correction, therefore there was no corrected bearing. The second one to note here is that since we do not have any corrected bearing, we use the distance and the forward bearing to get our delta nothing and our delta easting. Hope it's clear. Alright, you said it's clear. Now let's continue. So having gotten our delta nothing and our delta easting, we do not go for arithmetic sum. We do not go for arithmetic sum because we won't need the values. You know, the major or maybe one of the reasons why we get our arithmetic sum is because we want to use it to apply corrections to our what? To our coordinates here. But since we have already gotten to a point where we did not apply corrections to the angle, we know that almost all the coordinates we are going to have will be in error, but we don't know the particular station where the error will be. So we are not going to distribute any error. Let's just continue like that. There is nothing like correction. There's nothing like distribution of error on this first computation. So we move after getting our delta nothing and our delta easting. The same process we did to get our uncorrected coordinate. The coordinate you started from plus or minus the nothing value, the delta nothing value, and then we got up to this point. If you don't really get how we got to this point, the videos are there on the playlist. You can just go back there, understand the beginning of traversing, how we started, arrangement of your controls, and so many other stuff. So now, what's the way forward? The way forward is very simple. We are going to perform a reverse computation. We are going to perform what? A reverse computation. Now, how do we carry out the reverse computation? The reverse computation is very simple. The idea behind carrying out the reverse computation is that you will have to start from the control where you closed. Remember that we closed our traverse on what? On kg21. So on the reverse computation, we are going to start our traversing, or our computation rather, from kg21. That's another point to note. We've stated 3 points now. I think this is the third point. The third point we just stated now is that we are going to start a reverse computation. And on the reverse computation, we are going to start from the control where the traverse closed. This is the normal traverse computation. If there was no blunder, we would have gotten to this point, gotten our corrected, check our uncorrected coordinate with our corrected value. If they are okay, we distribute and everything would have been okay, as we stated on our previous videos. But since this is blunder and want to detect where the blunder is, then we are going to carry out a reverse computation. And the third point, or the third point, the third salient point we are trying to state here is that on the reverse computation, we are going to start from the control where this first computation closed, which is what? Which is kg21. And another point to note is that the observed angle on each of those stations, the observed angle at each of those points will now be like the external angle of the first angle we got. I know this one will be a little bit like jargon, but now let's get to our field book, or let's get to our computation sheet. So now, for instance, now let's use this value. On PT2, we observed an angle of 280 degrees, 00 minutes and 47 seconds, isn't it? So now what I'm trying to say, or the explanation I made, that on the reverse computation, the angle will be like the external angle. What I'm trying to say is that whatever angle you get for the first computation, on the second computation, it will be what? 360 degrees minus any angle you get. That will be the angle you are going to use on reverse computation. I hope we are together. Please, if you're missing any point, you can always pause the video, go back, and then you will get it. So now, what I said summarily is that we are going to do what? We are going to start a reverse computation. And on the reverse computation, what we want to do is that the first thing is we are going to start the computation from the control where the first computation closed, which is kg21, which is normally where the traverse closed, kg21. And the second thing on the reverse computation is that all our observed angles will be 360 degrees minus the observed angles we add for those stations in the first computation, which is what I just used. This observed angle was the observed angle we got for PT2 here, for point 2. The observed angle on point 2. So for our reverse computation, it will be 360 minus 280, 0047. Alright, now let's get back to our field. So the first thing is that we are going to show where the traverse computation is going to start. So to show where the traverse computation is going to start, let's just rule our normal line, like we are drawing a field book. Let this serve as the first line. Then, okay. So now we have designed the computation sheet for the reverse computation, and we have actually labeled them accordingly. So remember, there were some key points I was trying to let us understand, that the reverse computation is going to start from where? From the control where the first computation closed, and from our field, our computation sheet rather, we saw that the first computation closed on kg21 here. Therefore, the reverse computation is going to start from kg21. And then if it is going to start from kg21, then it's going to move from kg21 to what? To 0.4. From 0.4 to what? To 0.3. From 0.3 to 0.2. From 0.2 to 0.1, and then from 0.1 back to what? Back to kg22. And again, I also made some points clear to us that on the reverse computation, our observed angles will be what? Will be 360 degrees minus the observed angle we had for the first computation. Now, on kg21 for the first computation, the observed angle we had was 232.4107. But for the reverse computation, the observed angle we are going to have now, or we are going to use rather, will be 360 degrees minus what? Minus 232.4107. So these are the observed angles we are going to use for the reverse computation on each of the stations, not the observed angles we got from the field. Hope we are clear. It's all right. So now let's put these values on the computation sheet now. Now we are done filling in the observed angles for each of the stations on our reverse computation. The reason why I am emphasizing on this is because this is where most times students find it difficult to understand. I spelled it out here that the observed angle for the reverse computation will be gotten as what? As 360 degrees minus the observed angle you get for the first computation. And for each of the stations, we have calculated the value and we've got the difference here. So these are the observed angles we are going to use. And another thing is that students used to make this mistake that angles are observed like, let me leave the analogy. Students used to make a mistake that, okay, since the first angle here for the first computation is 232, then they are going to say 360 minus 232 degrees. No, you need to know that all angles are observed on a point, and it is the angle observed on a point that on each of those points rather that you are going to subtract from 360 and not the other way around. Now, having made that emphasis, let's now continue with our computation. Now, on this computation sheet, you will find out that we wrote the coordinates of what? kg21. The coordinates of kg21 is this. And if you recall from our first computation, the line between there's a line between kg21 and kg22. And that line was actually the line we started our computation with from our first computation here. So that 210 was actually the back bearing of 30. So if you really don't understand this, the videos are there. You can just go back and then you watch it and you get it. So the 210 we have here as a back bearing was as a result of the 210 we had here as a forward bearing rather was as a result of the back bearing we got for 30 degrees. Because if 21 to 22 is 30, then 22 to 21 will be 210. Having established that point, we are now going to continue with our with our computation. So if this is 210, then 210 minus 180, which is going to be the back bearing for this observed for this new station of what? Of kg21, it will be what? 210 minus 180, and 210 minus 180 is what? Is 30. So having gotten 30 here, we are now going to carry out our computation normally. So the most important points you need to understand on this reverse computation are the points I have stated out. First of all, you are going to start the reverse computation from the what? From the control the first computation closed. And in this case, our first computation closed on kg21. And the second thing is that the observed angles you have for each of the stations for the reverse computation will be the observed angles you got for the first computation, subtracting it from what? From 360. Each of those angles from 360, and which is actually what we did on this part of our seemingly the field book we are using now. So 360 degrees minus 232, and we did it down to this point. So the next thing we are going to do here is something we've already done, the forward computation. And I believe you understand the processes on how we are going to carry it out up till what? Up till the coordinate point. Now we are done with the reverse computation. The process of carrying out the forward computation up to this point, getting your forward bearings, arrangement of distance, getting your partial coordinates have actually been discussed on our previous videos. So now there are some things I need to explain here again for emphasis. Now on this particular computation, we remember that on the first question, when we got to this point, our misclosure was very big. Therefore, we did not distribute our error. We did not even compute for it when we found out that it was very big. After we computed rather, and we found out that it was beyond allowable error. Not just that it was big, it was just more than the allowable error. What did we do? We had to leave it, and we did not distribute the error. We did not get corrected bearing. We just used our forward bearings and our distances to get delta nothing, delta isting, and we continued. Same thing happened to our coordinates here. We did not care to do what to compare with the given value, because we know that almost everything we are doing from here, there has been a blunder. So now the same thing happens to the reverse computation. Now we have explained how we got our bearing here, then the back bearing up to this point. Now getting your distance. Now the distance is another place I will need to make some explanation, because I have had encounters with some colleagues that are still mixing it up. Now what you need to understand is that this is a reverse computation. We are starting from the end to the beginning. So now if you look at it, we have from station 21 to what? To 0.4. And on the first computation, it was actually from 0.4 to what? To 21. So if you look at this now, you find out that there is a place where you have from 0.4 to 21. And there's a place where you also have 21 actually starting. So sometimes people will make a mistake and we use the distance you have here. Now I know there is no distance here because this is actually a check line or a control line. So we don't have any distance. So now let's go to somewhere we will have a distance so that we know that we don't make that mistake. The second line we have here is what? From 0.4 to 0.3. However, on the first computation, we add it as what? From 0.3 to 0.4. So another mistake people used to make is that if you now look at from 0.3 to 0.4, the distance we have is 249,531. And then from 0.4 to 0.3, the distance we have here is 249,531. But some people used to make a mistake and they will say, since there is 0.3 here, and then we are moving this way, and then there is now 0.4 here for the reverse computation, they are going to use this angle here. No. The angle you are going to use is the angle on the station you are, because angles are measured on a point. So since angles are measured on a point, and then we have from like what we are on 0.4 to 0.3, and on the first computation we had it as well from 0.3 to 0.4. So we are going to use this, the observed angle we have on 0.4, and not the observed angle we had on 0.3. And if we say we are using the observed angle we had on 0.4, the observed angle we had on 0.4 here is 293.1735. So since we are still on 0.4, and that's the angle we are going to consider, we come to where we stated the angles for the reverse computation, which is 293.1735. By the time we find the difference, we have 66.4225, and that's the 66.4225. So that was the same thing that applied down. So now we did the forward computation and we got to this point. Remember, from the beginning we have been emphasizing that we want to know the point in which the angle was observed in error. However, I did not state the type of error it is. So now I want to state that the error we had was an angular error. How did we know that it was an angular error? We know that it was an angular error because when we got to this point on the first computation, the allowable error here was beyond the limit. Therefore, we know that it is now an angular error. So whatever we are doing, we want to know the station where the angle was observed in error, either observed in error or booked in error, or whichever the case was. So now, how do we know it? We have carried out the normal computation, and then we've carried out the reverse computation, and these are the coordinates of each of the points we had. Now on this sheet here, we have the coordinates of each of these points in the reverse computation, and on this sheet here we have the coordinates of each of those points in the first computation. So how do we know the station or the point in which the angle was measured in error? We try to compare the coordinates. The coordinates which are very close on the two observations, that is the point where the angle was measured in error. The coordinate of a point on the two observations which are very, very close. So now let's go. We have point 1 here. On the first computation, we have 860,205 for our northern. And then for point 1 here, we have 860,095.169. That's quite far for northern. Let's check eastern. We have 599,926. And then for eastern, we have 600,202. That means it's definitely not point 1. Now let's go to point 2. On point 2, for the northern, we have 860,249. And on point 2 here, we have 860,195. Then for the eastern, we have 599,856. Then here we have 600. So definitely it's not point 2. Now let's go to point 3. On point 3, for the first computation, we add what? 860,044. Then on point 3 here, we add 860,286 on this point 1, point 2, point 3. Then for the eastern, we have 600,045. Then for the eastern, we have 600. Definitely it's not point 3. Now let's get to point 4. What do we have on point 4? On point 4, for this particular session, we add 860,044.94914. And in this case, we have 860,044.201. Their difference is just in decimal. So the northern is sterling. Now let's see what we have for the eastern. For the eastern, on the first computation, we add 600,106.270. And then we have 600,106.162. So we can now say that the angle was actually measured in error on what? On point 4. The reason being that the coordinates we got from the both computation, both the first computation and the reverse computation, are almost close or are very, very close. You can see we have 860,044.208 and we have 860,044.914 for the northern. Then for the eastern, we have 600,106.162 and then we have 600,106.207. So we can now say that the angle measured on point 4 was in error. I hope this point is very clear. So that's how you are going to detect a blunder on your traverse computation, or maybe your observation from site. It is either the angle was booked in error or it was measured in error, or whatever case it is. So now, for the sake of, let's say for clarity, I'm going to compare this field book with the first field book we used, that the angle was, that our computation was within the allowable limit. You know, if you look through, you find out that the data there, they are almost the same as the data we got on our first computation, like the data we used for our first computation. So now, I'm going to bring that field book, which is this. So by the time we check out, we'll find out that the observed angle on point 4 or station 4 is the difference we have between these two field books. You see, we have 232, we have 165, we have 280, we have 281. But on point 4 here, this was the field book we used, and we had the allowable error. We went to our coordinates, we got everything correctly. We have 188. But on this particular one we used, that is now giving us issue, we add 293. And then when you come to KG21, you still see 291. The distances are all the same. So you can now see that either the booker booked a different value or the observer observed a different value. Whatever the case is, we have now seen that it's actually on point 4 that the angle was measured in error. So thank you very much for coming to our channel today. Thanks for watching. Your comments are very much welcome. Drop your comments there, like this video, subscribe to our channel, invite your friends to come and do the same, and I believe we are going to see you soon on our next video. Please take care of yourself.